Another application of derivatives can simply just be linear approximations. Okay? So we've seen that a curve lies very close to its tangent line at point of tangency. So here this is the f of x is blue is the curve. This red is the tangent line to the curve at this point of tangency right there. If I were to zoom in to that point of tangency, I really wouldn't be able to tell the difference between the curve and the line. Clearly, from this standpoint, you see there's a difference between the curve and the line. But if I looked very close to this point, right around here, I really wouldn't see much difference between the curve and the line. Why? They would have the same values, x and y, right there. I mean, the point and the line share, the curve and the line share that common point. So the x value and the y value are the same. When I plug x into the line, I get the same y values when I plug x into the function. Also, the change in the curve and the change in the line at that location are the same. So the slope is the same. The change in y with respect to x is the same right here. And so I really wouldn't see much difference between the curve and the line. So what that means is that if I want to work with this function, specifically at this location, I can approximate the function with this line. And as long as I stay relatively close to that point, then the function and the line should be very good approximations of one another. Okay? Now, the further I move away from that point, clearly there's a difference between this curve and this line. So over here, there's a bigger difference between them. But in the proximity of that point, they are very close to the same. So what we can do is if we want to calculate, say, f of a of a function, but maybe that's difficult or even impossible to do, we could simply compute nearby values of f with the tangent line and find a comma f of a by using the tangent line instead of the function itself. So we've seen the equation of the tangent line to a function of f at a comma f of a given by y minus f of a equals f prime of a times x minus a. That's basically just using that right there is using your y minus y1 equals m times x minus x1. Your basically point slope formula. You know, here this is f of a and a. Okay, there's your point. And this is the derivative at a. Okay, the slope. And so we could just simplify that a little bit more, move this f of a to the other side, and what we would get would be this equation right here, okay? And so this is basically saying y equals f prime of a times x minus a plus f of a. And this is what we call the linear approximation or the tangent line approximation of f at a. So essentially the function can be roughly approximated with this tangent line, okay? And we also could call this the linearization of the function. Okay? The approximation of the function, the linearization of the function, essentially flattening out the function to a line using this formula. So these can be used in a lot of different places. Lots of times they're used in physics. Okay? Say in analyzing consequences of an equation, and a physicist maybe needs to simplify a function by replacing it with its linear approximation. So, you know, you're working with something fairly complex, but you want to simplify it. You could use the linear approximation to simplify it. So, you know, if we're deriving a formula for the period of a pendulum, you know, physics textbooks would obtain the expression that a sub t equals negative g sine of theta for the tangential acceleration. And then what we could do is we could say, well, that's fairly difficult with the sine function there. And theta, okay, being this value that we're working with. So what we could do is we could just approximate it and say, well, sine of theta is actually pretty close to theta itself, if theta is not too big. When we look at the tangent line equivalent to sine of theta, so what we could do is instead we can look at it in this form and say, well, a sub t equals negative g times theta instead of sine of theta. And, you know, that could be done quite a bit to simplify some of the formulas that we're working with. And it's all it is this tangent line approximation. It's swapping one function out for essentially the tangent line equivalent to that function, the linear approximation. Theta is a linear function. Sine of theta is not. But the linear approximation of sine theta would be theta itself, as long as theta is not too big. And so that makes this formula much simpler. I mean, we could do this in optics. We could do it in lots of applications. A lot more would happen in 3D instead of 2D. So you could see this a lot more in Calc 3, where we work with 3D calculus. And what we do is essentially a linear approximation is a plane instead of a line. But again, just a quick little application of derivatives as they relate to the tangent line.